Okay, so further continuing with lemmas 9 and 10 in this lecture. Again, I'm showing you as we go along how I'm picking off the parts of theorem 8, okay, how these lemmas are related to that theorem on page 114 in section 2.3. Okay, so lemma 9, which your book does not prove. Your book simply shows A implies B. Well, we're about to show B implies A. Oh, excuse me. Your book shows B implies A. We're about to show B. We're about to show B implies A. So right here, I should have put B implies A. Okay. Well, that's clear by just my writing that there. Okay, so now we're going to have it going in both directions once I prove this. Well, here's the proof. It uses this nice little property that we developed in our other lemmas, which is why we had the other lemmas, that if we start with A is row equivalent to the identity, remember what that means. That means there's some elementary matrices such that if you keep multiplying A on the left by the elementary matrices, you're going to get the identity matrix. But we had another, we had a lemma 1, that all elementary matrices are invertible. So that means I can take this star equation here, which looked like this, and multiply it on the left on both sides by ES inverse, E2 inverse, E1 inverse. Okay, if I do that on both sides of this on the left, I end up getting this. Because this just pinches and pinches. This times this is the identity, times the next is the identity, and it just compacts down to just saying A on the left-hand side. What's on the right-hand side? Well, the product of these matrices with the identity, which is just their product. Well, now we see why lemma 2 is so handy. Lemma 2 tells us that if we have a product of invertible matrices, it's also invertible. So therefore we have lemma 9, which is that A is row equivalent to the identity, proves that A is invertible, or that A inverse exists. So we've done both directions, A and B. Now let's look at lemma 10. Make sure you can see the top of that. Right. Okay, so lemma 10 looks like this. You start with, and lemma 10, by the way, has parts K, G, I, and H from theorem 8 in there. So I can come over here and cross those off. K, G, I, H. Okay. Sorry, if you come back for a second, you can see that up there, right? And you'll notice that we have pretty much everything of theorem 8 except part C. The part C is about pivots. It's very difficult to prove things involving pivots. So in my course, I don't prove things about, your book doesn't prove anything about pivots. I'm not going to prove anything about pivots. We don't need part C. We can do everything that we need to do in this course without pivots. So I'm just saying, ignore part C. So no pivots. Proved in the book. So no pivots needed in this course. Okay? All right. So if you're used to pivots for some other reason from some other class, say if you've taken Math 2318 before, that doesn't mean you can use them in this course. In this course, you can only use, in your proofs, the things we have proved, right? That's the understanding. So, of course, if you come up with some other theorem, some fancy theorem from another book, and you prove it right on your test, then you can use it, but that takes up a lot of time. So, focusing on what we have proved and using it to go forward with proof, we have this. lemma 10, which has parts K, G, I, and H of theorem 8 for reference. Okay, here's how it goes. If there exists what we call a right inverse, a matrix D, such that AD is equal to the identity, we can prove that that shows essentially that for all that the mapping is onto, that T sub A is surjective, because for all vectors in Rn, there exists, remember, T sub A goes from Rn to Rn, right? T sub A goes from Rn to Rn. So to show it is surjective, we just show that anything in here, in the codomain, has a preimage over here. So that's what we're doing right here. We're stating that that property gives us this one. Well, that by definition, that's saying that T sub A is surjective, or that the range of the transformation is equal to all of Rn by the definition of range. And we're going to show how that also gives us this, that the span of the columns, the column vectors of A, called the column space, is exactly equal to Rn. And of course, part of that is the statement that therefore the column vectors of A must span Rn. We're going to come back and use that property very nicely soon. What about their proofs? Well, let's see. So we're just supposing in the beginning that we have a square matrix, and suppose that there does exist some matrix D that acts like its right inverse. In other words, that A times D will give you the identity. All right, so that's out there. Now pick any vector in Rn, call it B. All right, and now cook up another vector X, which is D times B. Okay, why do we do that? Well, if we now multiply both sides of this equation on the left by A, look what we get. AX is equal to ADB, just using that. By the associativity of matrix multiplication, this becomes AD is being multiplied by B. But what is AD? We've assumed AD is equal to the identity. So that's equal to the identity times B, or just B itself. In other words, we've just shown that for any arbitrarily chosen vector in Rn, there does exist some X. We cooked it up by multiplying that one by D, such that AX will be equal to B. Well, that's the same thing as saying, since T sub A of X is equal to A times X, we've just said that for all vectors in Rn, there does exist a preimage of that vector B called X under the mapping T sub A. So therefore T sub A is surjective onto, and by the definition of range, so can you guys see this? By the definition of range, what's the range? You should know that. Remember, we proved that's a subspace. If T is a linear mapping, right, which T sub A's always are. So the range, set of all vectors in the codomain, such that they have a preimage in the domain. Well, we just showed that that is every vector in Rn. So T sub A is surjective is the same thing as saying that the range of the transformation is all of Rn. Okay? So what have we got? We've gone from 1 to 2 to 3 to 4. Oops, now we have to go to 4. 3 to 4. What does that look like? Going from 3 to 4. Put that here. Okay, so from 3 to 4, what does that look like? We're assuming T sub A is surjective, and we're going to show that the column space of A is all of Rn. Okay. So T sub A surjective, we just did down here, is the same thing as saying that the range of T sub A, excuse the noise, is equal to all of Rn. Sorry about all the noise. And what do I want to show that means? I'm going to show that that gives us that the column space of A has got to be exactly Rn. Okay, what is the column space? So recall the definition of column space. Column space of A is just equal to the span of the column vectors of A, which I called A1 through AN back there. A1, A2 through AN. So their span is what we call the column space. That's just the same thing as the set of all linear combinations of those, right? So this is just equal to the set of all such linear combinations of the AI, I going from 1 to n. All of them. That's what the span is made of, all those linear combinations. And, well, if you remember, each one of these is the same thing as saying all of these. If we set x equal to column vector with C1, C2 through Cn, its components. Excuse me, I have to go glare at somebody in the kitchen. So if x is equal to the column vector with all the Ci in it, then that linear combination is the same thing as saying this. Remember we showed that. And so we have, what do we have? Let's see, train of thought, right. Okay. Well, that means that the set of all these images under the T sub A map, well, that's equal to the column space of A. Well, the images of all the images of T sub A means we're talking about the range of T sub A. And so we have the range of T sub A is equal to the column space of A. Not my best proof, but I think you could see what's going on there using all the previous definitions or some of the definitions we had from a while back, say in February. Okay, but what is the range of T sub A? We proved in 3, which we're assuming here, that that's equal to Rn. So that gives us that the column space of A is equal to exactly Rn. It spans all of Rn and doesn't go any farther. It's exactly that. All right. You'll notice that this also implies, therefore, that the column vectors of A span Rn. Right? They have to. If the column space is equal to Rn, then this has to be true. And that's statement number 5. So we're done. Okay, so what have we shown? Of theorem 8, theorems 9 and 10 have added all these other components in there. Again, we're not doing C at all because that is some sort of namby-pamby statement about pivots, which the book doesn't even prove. So don't use pivots.